Hello, sir. You are not audible, sir.
So a cycle is a non-trivial tail closed tail in a graph G. It's called cycle if its origin and the internal vertices are distinct. What does it mean? What is the definition of tail we have seen? Where we have seen that every edges are different or vertices are different. Vertices are different. Okay, then it is called. Yes. Tell me, what is the definition of a walk and
Ages are
part?
different.
So a tail in which the every edges are different, then it is called tail, and it is a closed tail. That means its terminals and the origin is the same. But it's also making one more condition that the origin and the internal vertices are also distinct. Okay, so that is called cycle. In detail, if I can say, the closed tail I'm denoting this closed tail by C is V1, E1, V2, E2 up to Vn, and then again some edges will be there. Let's say En, and then it is E1, sorry, V1, because the origin and the terminus, it has to be a same vertex. Is a cycle. This is known as a cycle if the first one C has at least one edge. That's the meaning of non-trivial cycle. The meaning of close means the V1, that means origin and the terminus is the same. Its origin and the internal vertices are distinct. That is the second condition that we can make is V1, V2 up to Vn are n distinct vertices. So if a closed tail which having this situation which satisfy these two conditions, that is called cycle. A K cycle, I will give you an example of a cycle in a minute. A cycle of a length k it's called a K cycle. A cycle of a length k, it's called K cycle. Now, a cycle is an odd cycle or even cycle. It depends on the what is the value of k, or whether it is a even k is an even number or odd number. So it depends on this. and it is denoted by, this K cycle is denoted by Ck. For example, if you want to plot C3, C3 means a cycle with a length of the cycle should be 3. So this is a C3. Because a length is 3, if I start with this internal and the terminals is the same, so this, you go in this manner, it will reach to the same point, and the length will be 3. What is C4? C4 is a square. This is a C4. C5 is a pentagon. This is C5. C6 you can plot yourself. What should be C6? So these are the cycles. Example of a cycle. Now, if you graph, suppose this is the graph, and some graph will contain the cycle, some of them will not contain a cycle. If I can consider V1, V2, V3, V4, and this is V5, then this, now I will not write the ages name because understood that in between V1 and V2 there is one age. So I can just denoting this situation as V1, V2, V3, V4, and then again V1 is a 4 cycle. So this graph contains a 4 cycle. If I consider, so I can say it is C4. C3 will be starting with any of this vertex, you can say. Let's say I am starting with V1, then V5, then V2, again we come to the V1. So this is the, this triangle is there. So it is a cycle, or I can say it is a 3 cycle. So that's why it is C3. So in general, this is this graph is contain a cycle that will have an example. So if I have a loop at some point or at some vertex here, let's say this is the loop, then a loop is just one cycle. One means a length of that, so it has only one age. So it is the cycle V4 V4. So it is as per the notation. Two parallel edges if I have like this, two parallel edges, is 2 cycle. For example, C2, if I can say, that is C4 goes to V3, sorry, V4 goes to V3, and then again V4. So it is V4, V3, V4. So this is C2 cycle. Okay, then after learning the cycle, there are certain results which we are not going to prove here, but we need to understand what is the statement is there for this theorem. Given any two vertices U and V, so if you pick any two vertices U and V of a graph G, in any graph G, if you pick any two vertices, and if there is a path in between U and V, then there will be a, sorry, if there will be a walk in between U and V, then there will be a path in between U. So that says that then UV walk contains UV path. It's understood that what is the definition of a path says every ages are different. That is the definition of age is there. No. The definition of path is, tell me, every. So that is a, there should not be a confusion between walk, tail and path. A walk is mixture of everything. Tail means every ages are different. Path means every vertices are different. Please don't confuse. So yourself. What is a path? It's saying that every ages are different in that. What is the statement? It is saying that every walk contains a UV path. If there is a path in between, suppose this is the vertex U and here it is a vertex V. If there is a path in between U and V, and at this point maybe some of the vertices are different or they are repeating, and so it is visualized that every walk contains always the UV path. Next result we'll try to prove using the mathematical induction, which tells you that the minimum number of edges in connected graph with n vertices is n minus 1. So what is this statement says that if you consider any graph with n vertices, and what is the possibility of a minimum edges in that graph? So the edges should be always n minus 1 if you want that minimum edges over there. We'll prove this result using mathematical induction. So what is a mathematical induction? Let us recall those who don't know. If you want to consider any Pn statement which you want to prove for n is belongs to natural number, that means you have to prove the statement which is true for any natural number, then you have to follow the 3 steps. The first one is you have to prove P1 is true. First thing, you have to prove that P1 is true. That means for n equal to 1, the statement is true. The second, you have to assume Pk is true. In between 1 and n, you can assume that Pk is true. And the third statement, you have to prove Pk plus 1 is true. And any statement will satisfy these 3 steps, then we can say that the statement is true for any natural number n. Here, what is the statement? A statement says this, the same statement which we have written, that the minimum number of edges in the connected graph G with n vertices with n minus 1 edges. So we shall use or we shall prove this result using mathematical induction. What about with n vertices? So first statement is to prove that the statement is true for n equal to 1. That means for P1 it is true. If the graph contains 1 vertex, then how many number of edges will be possible? Obviously it is 0 if it has only 1 vertex. So we can write that for n equal to 1, the result is true. Second statement, you have to assume the result is true for pk. So for, let's say that let m be the number of edges of such graph. Okay, so I'm just assuming that m is the number of edges of the such graph. What we will show that we shall show that for m greater than or equal to n minus 1 is there. We'll show that m is greater than or equal to n minus 1 by mathematical induction that we will do this. So now let us consider clearly then m is greater than or equal to n minus 1, let the result is true for m equal to 0, 1, 2, 3 up to k. What I have told you that you have to assume the result is true for p equal to k. Now we shall show that the result is true for m equal to k plus 1. So let G be the graph with k plus 1 edges. Let E be an edges of graph G. Now what I am doing is I am just eliminating this edge from this graph G. Then the subgraph G minus E has how many number of edges and how many number of vertices. So what we are doing is we are just removing or we are deleting this edge from the graph G. So deleting an edge in a graph G does not remove the vertices. It's only remove that edge. Originally this graph has how many number of edges? K plus 1 number of edges. Now as per this, if I remove one edge, then does this graph G minus E contains how many number of edges? K number of edges. And how many number of vertices? Vertices will be n. The vertices will not be changed. So it has k number of edges and n number of vertices. Now there will be two situations there, whether this G is connected or G does not connect, because suppose this is the edge E and over this there is some graph is there, and on this side also some graph is there, and if you remove this edge from this, then it may happen that there will be two component will be there, or it may possible that there is some path in between joining these two. If you remove this one, then that still the graph will be connected. So if the graph is connected, then by our hypothesis the result is true, because the hypothesis is saying that a minimum number of graph with the connected graph has to be connected with n vertices is n minus 1. So it has n vertices now. So it has minimum n minus 1 number of edges should be there. So if G minus E is also connected by our hypothesis, K is greater than or equal to n minus 1. That means K plus 1 is greater than or equal to n minus 1 plus 1, which is equal to n, I can say. If I add 1 here, both sides. Now the second situation is where this G minus E is disconnected. That means if I remove this edge from this, then the graph will have two components. The first one is this, another one is this one. Now in that situation, what will happen? Disconnected, then it could have two components. And both these components are connected components. So let's say this is the graph with n1 vertices, and this will have n2 vertices. So as per the result, and it has k1 number of edges, this will have k2 number of edges. As per the assumption, what is our assumption? That if any graph with k vertices, n vertices will have k number of edges, that means minimum number is here, it is k1, here it will be k2. Okay, where k1 plus k2 is nothing but the k, and n1 plus n2 is nothing but the n. So that we can write, let the two components have k1 and k2 number of edges. And n1 and n2 number of vertices. Respectively. Now, so by our hypothesis, k1 is greater than or equal to n1 minus 1 and k2 is greater than or equal to n2 minus 1. We can have. If I add this two, why this is used? This is true using the PMI, as we have told you that the result is true for k minus 1 and the less than that. So for we are using that condition here. And if I add this two, that will give you k1 plus k2 is less, greater than or equal to n1 minus 1 minus n2 minus 1. So this will give you n1 plus n2. So therefore we have k1 plus k2 is greater than or equal to n1 plus n2, but k1 plus k2 is nothing but the k, and n1 plus n2 is nothing but the n. So sorry, this is plus n1 n2 minus. So this will give you minus 2. But this is minus 2, so it will say is again this n1 plus n2 minus 2 will be again greater than or equal to n1 plus n2. That we can write, definitely we can write, because this is, we are subtracting minus 2 from this. So hence we have k1 plus k2 is the number of vertices in the first component, k2 is the number of, sorry, edges in the, k1 is the number of edges in the first component, and k2 is the number of edges in a second component. So k1 plus k2 will gives you k, and n1 plus n2 will have n. So that means it will gives you k plus 1 is greater than or equal to n plus 1. So that means number of vertices is always smaller than this n minus 1. So thus we can say that the result is true for m equal to k plus 1, and that's completes the proof of any graph. The minimum number of edges in a connected graph with n vertices is n minus 1. Next theorem is a graph G is bipartite. We already discussed what you mean by bipartite graph. That means there has to be a partition of the vertex set in such a way that one edge is in one set, another. So there is a every edge has one end in one part and another edge is in another part. That is called the bipartite graph. And if you want to check whether the graph is a bipartite, and this result is gives you if and only if it has no odd cycle. If the graph does not have the odd cycle, then we can say that a graph is a bipartite graph. For example, if I want to say that find out whether this, so we are assuming this result using or without proof, but the application of this result is very good. So suppose that if you want to check whether this graph is bipartite or not, what you will do? As per this, it says that a G is bipartite if and only if it has no odd cycle. A cycle I already discussed. What do you mean by cycle? Odd cycle means it is an odd cycle. That means number of edges in that cycle will be odd. That is called odd cycle. If there is a no odd cycle in the graph, so can you find any odd cycle in this graph? All the cycles which are possible here, it is of C4 type. Okay, in this graph. So there is a no odd cycle is there. So that's why this graph is a bipartite graph. This graph is a bipartite graph. And now I'm asking you a same question, but slightly different one. Suppose this is the graph you have, and this is the graph. If I can plot, this is one vertex. Okay, is this a bipartite graph? I can call this as a G1, and if I call this is as G2. In fact, what is the situation is this G1 and G2, both of them are isomorphic graph as they are bipartite. You just also check that this Graph also does not contain odd cycles. This graph is also not containing the odd cycle, so that's why it is also bipartite graph. And this, in fact, this G1 and G2, they are actually isomorphic graph. It's plotting in the different manner. So that is
Excuse me, sir.
yes.
Can we call it the G2 as a complete bipartite graph?
It is not complete bipartite graph.
Yes.
It is not. Why?
Because odd one is not connected.
This one is not connect to this. This I should draw it with the real color. This vertex is not connect to this vertex, so that's why it is not complete bipartite graph. It is bipartite, but not complete bipartite. Okay. For example, this one is not connect to this. So that's the way it is not. Okay.